So in this project, like we are going to implement error tolerant adder for a 8-bit pixel depth image processing application. The main intention of this project is like we are going to implement the carry select approximate full adder. With the help of one application we are going to make it. So for that purpose they are providing all the equations under. So this is the basic architecture of the proposed CSFA. In this, like we will be using a two part of the design. One is like AND OR gate implementation in the first part, and second one AND OR gate 2. This two implementation will be done for the first part, and then based on the multiplexers we can able to select the sum and carry. So basically that adder having the full adder having the ABC, three inputs for us. So this three inputs from the BC will be given into the AND OR gate 1, and it will be providing the O and AO1, and here A will be given into that O will be get as output for the AND OR gate 2, and it will be providing the output OO2 and AO2. So this AO2 will be activated as a selection line for the multiplexer, and it will be selecting the sum and carry. So this is the table for the proposed CSFA. So first we need to implement this architecture. So this is the proposed CSFA architecture we need to implement. After implementing the CSFA architecture, we need to implement that the hybrid architecture for us. So that architecture is here. So here this is the architecture for us to implement the proposed ETA-CSAFA architecture. This is the 8-bit architecture. In this part, like we can able to divide it into the two part. One is accurate part, another one is inaccurate part. So in this inaccurate part only we will be adding our approximate CSAFA architecture, and in the original part, like whatever the CFA original carry adder, whatever the adder we have that adder will be using here. So two designs we are making here. This is for a 8-bit design. I'm just making this paper is implemented for the 8-bit implementation. I'm just going to implement 8-bit as well as the 16-bit. Both the designs we will be implementing. The area, delay, power calculation and all will done it for this architecture. So this is general architecture. From the general architecture, what we will be doing it as a modification, in the sense we will be adding this too. So here, like we will be using the for our last 2 bits, like we will be using only the OR gate and CHA in the sense it's conventional half adder, and CSFA in the sense it's a proposed hour adder, and CFA in the sense it's a conventional full adder we are using. So these, based on these three designs, we will be implementing the new architecture, and after implementing this architecture we are making for the testing verification circuit. So here the test vectors will be generated, an n-bit conventional adder and n-bit proposed hour adder, ETA adder, and whatever the results we will be getting from the both adder, it will be verified with the exact it will be verifying with the help of XOR table, will be verified whether it is matching or not. So this is what the complete idea of this paper. So for this paper I am preparing the synopsis. So that synopsis document is here. So here the synopsis will be there. So motivation, objective, and introduction, literature survey, and after that like proposed system, like the proposed system, how it is working, the truth table, whatever the thing I'm explaining right now. So everything I'm including into that. So these are like the proposed in this thing, like we are going to implement with the help of Verilog programming, and software we are using Models in 6.4c, and synthesis paper I am using a Xilinx 13.2 or 9.1, and hardware also we are using Spartan 3 I am using. So these are all the things like we are describing this synopsis. So after that the simulation we are going to explain here. So for this simulation, like I am just making the 8-bit architecture here. This is the proposed one, and here this is the proposed one, CSFA 1 based 2 architecture we are making. So in this design verification circuit also I made it. So after that the 16-bit design also we are implementing. This is conventional CSA and proposed ETA based CSFA, and for based on that we are making the comparison also. So here I'm just showing you like how it is working. So this is the design verifications code, and this is the proposed ETA-CSAFA code. This is what we implemented, and after that we are adding the design verification part also. So we are going to execute that code. So just open the code in the model sim, then we will do the simulations for that. So design verification system for 16-bit I made it. Clock reset and yes and error. Yes in the sense it's a sum output, error in the sense it's a error output. Whether it is error is there or not, it should be indicated. So first go to compile and click compile, and just select all the programs and click compile, give yes and done. So the compile process is getting completed. So once this compile process is completed, just go to simulate, start simulation, and inside the work folder you can select the folder like what you wanted to choose. So the file name is design verification system for 16, so you can choose that. So if you want to choose the adder design, you can choose this adder design. So we are going to choose this 16, just give OK, and then you can see the program. So in the program we are adding the test vectors to generate the test vectors, and after that the conventional CSA, and after that proposed CSFA, and after that we are finding the error. So how we are finding the error, in the sense both the data, whether it is matched or not, we will be verifying. If it is matched, the data will be 0. If it is error value is 0, no error. If it is 0 is not there, 1 in the sense the error will be find it out. So these are all the things we are made it. So like you can just go to now right click, add to a all items region, and below you will get the waveform. So in this waveform you can give the inputs here. Now there is no need to feed the input everything is get it from the directly from the test vectors. So we can give only the clock and reset. So the clock will be the right click and clock, just give OK, and then reset condition you need to give. So right click, force, and just give 1 initially. So after that, one time you can run it, then you can change the reset condition 1 into 0 and run it. So now you can get it like whether it is having the error or not. So all the data will be in the 0 only, the error data, so there is no error. In case if you wanted to add a error values, we can add it in the error. For the design we can find it out the error also. So here the sum value will be there, so sum value we will be find it here. So the test vectors 1 and test vector 2 will be the input for the adder, so we can check it out that. So 1 into 254, 1 plus 254, 255. So all the values like the inverted value, I'm just giving a one input and another input, so that's what the adder results will be 255 only. So this is the test vector. So here the sum for the conventional, this is sum for the proposed. We can verify the both from here. So this is what the complete design of this paper. So here I made it for the 16-bit. Similar way I made it for the 8-bit also. Even like we will be making a comparisons for that. So the documentation I just show you here. So this is the complete final documentation. So it's having the abstract, introduction, literature survey, everything with the results. So here the RTL schematic, technological schematic, power of the conventional power and proposed adder's power, and I just made a comparisons for that. So 16-bit adder, like how it is compared with the area, delay and power, everything I just made it in a tabular form here. So we can verify with this report. And the synthesis thing, like I'm just doing with the Xilinx software, so those results and all will be available here. So the paper they are implementing only the 8-bit, we are making a 16-bit as a modification. So that is a modification I preferred for this project. So in our organization we are providing the services in this way, and also code feature enhancement, explanation, execution, paper preparation and documentation, everything will provided us in a proper time. And these are all the specific domains we are specialized. And thank you.